Welcome back. In this video, we're going to talk about some theorems and theories that can contribute to our analysis of polynomial functions. We're going to look at about 5 theorems together today. 3 of them we have up here on the screen already. All of these are, think of them as tools that can help us identify the zeros of a function. Okay, so let's start with the fundamental theorem of algebra. It says that every function defined by a polynomial of degree 1 or more has at least one complex zero. Keep in mind that a complex number, or the set of all complex numbers, also includes real numbers. So that means that for every polynomial function, degree 1 or more, we're going to find a zero, whether it's a real number 0 or a complex number 0. Okay, we've talked about if it's a real number 0, that's going to give us an x-intercept where the graph would touch the x-axis. If it's a complex number 0, then the graph would not touch the x-axis. Okay, then we have the number of zeros theorem. A function defined by a polynomial of degree n has at most n distinct complex zeros. Okay, so distinct here means unique. Keep in mind that it's at most. The number of zeros is at most the degree. So if the highest power on x is a 5, we could have at most 5 zeros. If any of them were repeated, then we may have less than that. Okay, and then we have the conjugate zeros theorem. It says let f of x be a polynomial function having only real coefficients. So that's the criteria to apply this theorem. If we have real number coefficients, then when a complex number is a zero of the function, its conjugate is also a zero. A plus bi and a minus bi are called conjugates of one another, or complex conjugates. One of the properties that conjugates have is that if you were to multiply them together, these two, we end up removing the I and getting a real number. So it's sort of a complement in that way. Okay, so let's apply that to this example. For each polynomial, 1 0 is given. Find all of the others. Now we're going to combine what we used in the last video with regards to synthetic division to help us find the zeros as well. To be honest, I haven't tried to see if you could factor this. Maybe you could. Maybe you could factor this, but we're going to use synthetic division just to practice that. If you want to go back and do this example by factoring, by all means, go right ahead. Okay, so we're going to do our synthetic division with 5i. And we're going to put the 5i out front here. And we're going to list the coefficients and descending powers of x in that order. There are no missing powers of x here, so we don't have to put in a 0. Remember to do the synthetic division. Really what we're dividing by is x minus 5i. So when we divide by x, the degree goes down by 1, but the coefficient in front is going to stay the same. So we bring the 3 down. And then we multiply. 3 times 5i would be 15i. So we're doing the same process, but we're using complex numbers. And then we're going to add down. This would be negative 5 plus 15i. Notice I can't really combine these two numbers because the 15 has an I attached to it and the negative 5 does not. And then I would want to multiply this by 5i. Okay. Don't forget, I'll just write it off to the side. I squared is negative 1. So I'm going to do that part first. So if I did 5i times 15i, that would give me 75i squared. I squared is negative 1, so that would give me negative 75. And then if I did 5i times negative 5, I'll have minus 25i. I probably should have left a little bit more room. Okay, and so then we're going to add down 75 plus negative 75. Those are going to add to 0. So I'm just going to get negative 25i. And then I'm going to do this again. 5 times 25 is 125. I have I squared, which is negative, and I also have this negative, so that's going to become a positive 125 when I multiply it together. And then when I add these, I get 0. And because the question that we're working here tells us that 5i is a 0, according to the remainder theorem that we talked about last time, this is the remainder should be 0 because it should divide in evenly. Okay? Now, if we wanted to write out what we have, I'm going to do this on a separate piece of paper so that it doesn't interrupt the flow of our work. But by doing this synthetic division, basically we could rewrite f of x as x minus 5i. And then these numbers down here at the bottom, remember, are coefficients for the polynomial that it multiplies. And the degree is less by 1. So it was x cubed. We divided by x to the first. So now we have 3x squared. I'm going to do plus here and just do negative 5 plus 15i times x. That's the coefficient for x. And then minus 25i. Okay, that's a crazy polynomial. Now, if these were nice, maybe we could think about factoring what we have left, but I definitely don't want to do that. So we're going to use the conjugate zeros theorem. So I'll come back to this in a minute. I'm going to set this to the side again. Okay, so if 5i is a 0, then negative 5i must also be a 0. Because this is its conjugate. So we're just using that theorem that we were just talking about. So now I can take divide further. I've already divided 5i into the polynomial, so I don't want to use the polynomial this time. I would like to use the resulting coefficients I got at the end of this first step. So, and I'm going to space them out a little better this time. So I'm dividing further because I want to be able to divide out these two. These two are zeros. I want to divide out the factors that are associated with them and see what's left over. Okay, so I'm taking this. Was 3x squared. I'm dividing by x minus negative 5i. And so I'm going down by another power of x, but the coefficient is remaining the same. So I bring it down, multiply by negative 5i. I get negative 15i. These are going to add to 0, so that'll give me negative 5. Negative 5i times negative 5 will be positive 25i. And when I add down, I get 0. Okay, and again, because of the conjugate zeros theorem, we knew that this was true, and our synthetic division proves that because the remainder theorem says that it will be a 0 if I get 0 for my remainder, and I did. Okay, now let's go back to the factoring we did a minute ago. Let's see if we can fit all this on the screen. So I factored further. Now I have two factors. I have x minus 5i from the first step, and I have x plus 5i, or x minus negative 5i, and those two negatives would make a plus. And here's what I have left. I was at 3x squared, but I'm going to go down 1 power of x. So I have 3x minus 5 left over. Okay, so if I go all the way back to the beginning of the problem, it said for each polynomial, 1 0 is given, find all the others. So find all the other zeros. So I did my division, I did my factoring. To get the last 0, I could set this equal to 0. Maybe you could do that in your head, but I'll go ahead and write it out. Okay, so we have 3 zeros for this function. 5i, negative 5i, and 5/3. So this is one way that we can use the conjugate zeros theorem to help us identify additional zeros. And sometimes if we can work our way down as far as the power on x, then we can factor the rest or use what we have left to find the rest of the zeros ourselves. Okay, so that's the conjugate zeros theorem. Let's add to that something called the rational zeros theorem. The rational zeros theorem says, let f of x be a polynomial function with integer coefficients. So that's a criteria. If we don't have integer coefficients, then we cannot apply this theorem. Remember, integers are positive and negative whole numbers. Okay, and then if I can make the fraction p over q, where it's written in lowest terms, and p over q is representing a 0 for this function f of x, then it turns out that the p in the top of the fraction is a factor of the constant term. That means it divides evenly into the number part of our function, like this 10 here. That would be the constant term. And the q in the denominator divides evenly into the leading coefficient, which would be the number in the very front of the polynomial, in front of the highest power of x. Now it is kind of important to point out that this is an if this is true, then this is true, right? It's not the other way around. So it's not if they divide evenly into these things, then I definitely have a 0. It doesn't go that way. But it does say, okay, if I have a 0, then this will be true. So when I list all the factors of the constant term and the leading coefficient, and I make all the possible fractions, somewhere in that list is the 0 of my function. So it doesn't, it gives you a sort of confined set to work with. You're not trying to find the 0 in all numbers everywhere. Now you have at least a smaller set. Sometimes that set of possible fractions is a small list, and sometimes it's a large list, but it is a list nonetheless. So the theorem, the rational zeros theorem, will give a list of possible zeros that you can use then to test and try to find the 0. Okay, so let's try that out with this function. This one's from your book. We're in section 3.7. This is number 53. This polynomial we have is x cubed minus 2x squared minus 13x minus 10. Okay, and so this one, if you tried to factor, it has 4 parts, so you might think about factoring by grouping, but we can't find anything in common between these 4 terms, not even if we rearranged them. So this one is not factorable. With the tools that we have, it is factorable, but it doesn't kind of fit with the other problems that we've practiced and strategies that we've practiced. Okay, so we'll use the rational zeros theorem to help us find the zeros so that we can factor it. So let's start with listing out factors of the constant term. Okay, and for this problem, the constant term is the 10. Okay, so factors of 10. I tell you, let me write this off to the side. I usually do it like this. We can have 1 times 10, 2 times 5, 3 doesn't go in evenly, 4 doesn't go in evenly, and then we're back to 5. So it must be these 4 would be the factors, and they could be positive or negative. So we usually list them as a plus or minus. So I have plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. Those are all the numbers that would divide evenly into 10. Okay, then we would do the same thing with the leading coefficient. The leading coefficient for this polynomial is just a 1. It's sort of implied here. So factors, oh, you know what? This is going to be our P, and this is going to be our Q. Factors of the leading coefficient. We really just have plus or minus 1 as our options, which is fine because the smaller the list, the easier it'll be to narrow it down. Okay, so then the list of possible zeros. Is any fraction I can make where I take a number from the list of P divided by a number from the list of Q. Okay, so I could have 1 over 1, which would be plus or minus 1. I could have 2 over 1, 5 over 1, and 10 over 1. So this is what the rational zeros theorem tells us, right? If I look at all the factors here, then the zeros must be among this list. There are 8 possibilities here. Not all the possibilities are going to be 0, so I would need to test to try and find the zeros. So we're going to do that. Then this could be long and tedious, but that's just the way the theorem works. Okay, so I usually start at the beginning of the list. Usually the textbook is pretty nice and gives you at least 1 0 that's kind of in the beginning of the list so that you don't have to test them all. Okay, now you could test these in a lot of different ways. I'm going to use synthetic division since that's what we've been practicing. You could also plug them in. You could also use your calculator. Okay, the coefficients for our polynomial are 1, -2, -13, and -10. So I'm going to do the synthetic division, bring down the 1, multiply, and then add down. Multiply, and then add down. Multiply, and then add down. Okay, so I tried 1 to see if it was a 0. Is 1 a 0? And the answer is no, because in order for it to be a 0, I would need to get a remainder 0, right? So 1 is not a 0. Let's try -1. Okay, so I bring down the first number, multiply by -1, add down, multiply by -1, gives me +3, add down. This is looking promising. -1 times -10 is +10. And I got my 0 remainder, which makes me super happy because that means I found a 0. So -1 is a 0. Yay. Okay, So if we wanted to find the other zeros, let's go to the factoring, because we could continue testing if we wanted to, but I think using the factoring was probably a little bit quicker at this point. There's 8 possibilities in this small list. We tested 2 of them. We would have to test 6 more. I guess you could do that, but I think the factoring would be faster than that. If -1 is a 0, what is the factor? X minus -1. Those 2 negatives together would be an x plus 1, right? Remember, these are the coefficients of what's left. We were dealing with x cubed, but we divided by x plus 1. So now we're down by 1 power of x. This is x squared, 1x squared, minus 3x, minus 10. We're really hoping that this is factorable, and it is. Okay, so 2 numbers that multiply to be 10, 5 and 2 look really promising. We need them to add to be -3. So I want to have -5 and +2. Those are all the factors. We factored this polynomial. If we set each factor to 0, the zeros would be -1, +5, and -2. All right, very good. Hopefully that gives you an idea of how the rational zeros theorem can be used. I thought we could do one more, just because this one was a fairly simple one, and I thought we could pick one that maybe had a little bit longer list. Okay, so let's try another one. This one's also from your book in this section. This is number 59. Okay, so remember P divides evenly into the constant term. Let me just do it off to the side. I like to do it this way. I feel like it's a good visual. So we can have 1 times 6, or we can have 2 times 3. If we were to go on to 3, we already have 3 listed here. So these are the possibilities. So plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. And then Q divides evenly into the leading coefficient. This time that's a 12. So for 12, we could have 1 times 12. We could have 2 times 6. Or we could have 3 times 4. So let's list those out. Okay, and so the possible zeros that we could have would be all the fractions that we make where we have P over Q. So we could have 1 over 1. We could have 1 over 2. We could have 1/3. 1/4, 1/6, 1/12. Okay, so I did 1 over all these. Now I could do 2 over all of these. Some of them are repeated, so you want to watch out for that. So 2 over 1. 2 over 2 would be 1. We already have that. 2 over 3, 2 over 4 would be reduced to a half. We already have that. 2 over 6 would reduce to 1/3. We already have that. 2 over 12 would reduce to 1/6. We already have that. So we did all the 2's. 3 over 1. I don't know if I'm going to be able to fit this in one row. We'll come down here. 3 over 2. 3 over 3 would be 1. We have that. 3 over 4. 3 over 6 would be a half. And we already have that. 3 over 12 would be a fourth. We have that. Okay, 6. We have 6 over 1. 6 over 2 would be 3. We have that. 6 over 3 would be 2. We have that. 6 over 4 would be 3 halves. We have that. 6 over 6 would be 1. And 6 over 12 would be a half. So that's our list. Okay, so how many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And each of those have a negative. So really that's 24 possibilities. Okay, clearly we don't want to try 24 possibilities. All right, so we're going to start at the beginning of the list and hope that one of those shows up as a 0. Again, you could try, but I don't think the tools we have for factoring will allow us to factor this. It is factorable, but grouping is not going to work. Okay, so let's start with 1 and try it out. Okay, so we're going to divide by something that begins with an x, so the coefficient comes down, then we multiply and add down, multiply by 1, add down, multiply, and add. Our remainder is not 0, so 1 is not a 0. Okay, let's try negative 1. I'm going to bring down the 12, negative 1 times 12, add down, negative 1 times 8, negative 1 times negative 9, okay, so negative 1 is not a 0. Okay, let's try a half. Bring down the 12. 1/2 times 12 would be 6. Add down to be 26. Half of 26 would be 13. Add down would be 12. Half of 12 would be 6. Negative 6 plus 6 gives us 0. That makes us super happy, okay, because the remainder theorem says if this is 0, 1/2 is a 0. So we found one. Yay. Okay. All right, so now let's write down what we have. So if we take our polynomial p of x, because 1/2 is a 0, we have a factor, x minus 1/2. And this is what's left over. If you go all the way back up to the top, we started with x cubed. We divided by x to the first. So this becomes 12x squared plus 26x plus 12. Okay, I think we can factor this. Let's try it. If you got really desperate, you could use the AC method. Okay, it's a little bit more work, but sometimes that's worth it. All right, so I tried this out. You could try some different things, right? We've already got a list of the multiples that numbers that multiply to be 12. I'll just fill in what works here, okay? 3x and 4x work in the front. And then 2 and 6 in the back. That way, on the outside, I have 18x. On the inside, I have 8x. 18 plus 8 adds up to 26. Everything's positive here, so all pluses. Okay, now to make this look even better, notice this the last parentheses here, 4 and 6 have a common factor of 2. So I'm going to factor that out so you can see what that would look like. Okay, and then I'm going to move it to the front. I can do that because it doesn't matter where it is, right? They're all multiplied together. It doesn't matter the order. I'm going to move the 2 up to the front. And then I'm going to multiply that 2 by this factor so that I don't have to have a fraction anymore. So then I'll have 2x minus 1. And keep in mind, if I set this equal to 0, when I solve for x, I get a half. If I set this equal to 0, when I solve for x, I get a half. So I haven't changed anything in regards to the 0. I'm just writing it in a different way. Okay. I ran out of space here. Let me put it up here. All right, but if we were to set each part equal to 0, our zeros would be 1/2. If I set this middle one equal to 0, I'd have negative 2/3. If I set this last one equal to 0, I'd have negative 3/2. This one took a little bit more work. It could have been way harder. But so the rational zeros theorem, it gives us some information. It doesn't give us everything. So we do still have to put in some work and test to see where the zeros are. But once we get it down to something that has an x squared, usually at that point, if it's factorable, we can continue factoring and find the rest of the zeros on our own. Okay, one more theorem to look at today, and that's something called the Descartes rule of signs. And it reads, let f of x be a polynomial with real coefficients and a non-zero constant term written with descending powers of x. Okay, and you get all that criteria, real number coefficients, and it has to have a constant term that's not 0. Then we can talk about how many positive real zeros it has and how many negative real zeros. This is not talking about complex zeros. That's probably worth noting. Okay, so the number of positive real zeros is either the number of variations in sign occurring in the coefficients. So we look from left to right, from one coefficient to the next, and we see, does the sign change from positive to negative or negative to positive, and if so, how many times, right? The number of times it changes. It could be that number, that could be the number of positive real zeros, or it could be less than the number of variations in sign by a positive even integer. Let's make up an example so I can show you what that looks like. I'm just going to make something up. Let's say f of x is x to the 5th minus x to the 4th plus x to the 3rd minus x squared plus x minus 1. Okay, so keep in mind there's a positive 1 here, so we're going from positive to negative, that's one sign change, negative to positive, that's 2 sign changes. Positive to negative, that's 3 sign changes. Negative to positive, that's 4. Positive to negative, that's 5. So we changed sign 5 times. So the number of positive real zeros for this could be 5, or it could be less than that number by a positive even integer. So that means I could subtract 2. It could be that I have 3 positive real zeros, or I could subtract 2 again. It could be that I have 1 positive real zero. Okay, so like the rational zeros theorem, it does not tell us what the zeros are. It does not always give us a definitive answer, but it helps. Okay, the number of negative real zeros is also the number of variations in sign occurring in the coefficients, this time of f of negative x, or is less than the number of variations by a positive even integer. So let's try f of negative x. Usually we have to calculate what that is. Let's just use this example I made up. Oops. Okay, so if I raise negative x to the 5th power, still going to be negative. If I raise negative x to the 4th power, it's going to become positive, but I already have a minus sign here. So that stays. If I raise negative x to the 3rd power, it becomes negative. If I raise negative x squared, that's going to become positive, but I still have a minus here. And this is a negative x. And this is a negative 1. Oh, this is turning out to be a very boring example. I'm sorry. Okay, so in this case, we don't have any changes in sign, so there would be 0 negative real zeros. Okay, if I picked a better example, okay, and we counted, right, it works the same as this. If we had 5 changes, it could be 5. Or if we had 4, it could be 4, 2, or 0, right? And so it just sort of counts down that way. This actually gives us a lot of information. We're going to combine this with the rational zeros theorem. So if there are 0 negative real zeros, that knocks out half of our list of possibilities. Okay, so alone, it doesn't give us a definitive answer, but it does give us a clue. So let's do one last example so you can see how this would work. This is number 56 from your book. Okay, so let's apply the Decart rule of signs. So how many sign changes do I have? Just one in the function, right? I'm going from positive x cubed to negative x squared, and then it stays negative, stays negative. So I have 1 positive real 0. Okay, now let's find p of negative x. So that's going to be negative x cubed. This is going to make this positive, but I still have a minus, so it'll be minus x squared. This becomes a plus 10x minus 8. So the changes in sign, I have 1 right here and 1 right here. So 2 variations in sign means I could have either 2 or 0 negative real zeros. So I'm not sure if I have a negative real 0. It could be 0 or it could be 2. but I am sure that I have one positive real zero. So it would be best for me to check all the positive possibilities. Okay, now let's apply the rational zeros theorem and put these together. So let's put the possibilities for P and Q. Remember, P divides into the constant term, so factors of 8 would be, we could have 1 times 8 or 2 times 4. So plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. The coefficient for x squared cubed here in the front, the leading coefficient is a 1. So Q could be plus or minus 1. If we form all the possible fractions P over Q to make our list of possible zeros, everything's just going to be over 1. So we have these 8 possibilities. Okay, and if we add that together with the information we found using Descartes' rule of signs, we know that we're guaranteed to have one positive real zero. So it would be worth it to check the positives first, because one of these 4 positives must work out. Okay? So let's try that. Let's start with 1. We'll do the synthetic division. 1 times 0 is 0. 1 times negative 10 is negative 10. All right, 1 is not a 0. Let's try 2. As you practice this, it'll come faster to you. 2 times 1 is 2. We add down. 2 times 1 again is 2. 2 times negative 8. All right, so far, not a 0 yet. Let's try 4. Four times 1 is 4, add down. 4 times 3 is 12, add down. 4 times 2 is 8. There we have it. So 4 is a 0. Okay, if we wanted to wrap this up by factoring it, our P of x has a factor of x minus 4 because 4 is a 0. It was x cubed as the dominating term or the degree, so now we're going down by 1. So this would be x squared plus 3x plus 2. That's definitely factorable. And if I were to factor it all the way, we get x plus 1 and x plus 2. So my zeros are 4, negative 1, and negative 2. All right. Well, I hope this gave you a good picture of how these theorems all work together to help us find the zeros of a polynomial. We'll definitely take some time to practice these in class, and I hope that you'll try them out for yourself at home as well. Thank you.